Good morning. Hope you had a good, productive weekend. Excuse me. I know it's hard to keep up the intensity here. It's been a long quarter, but this is our last week of classes. And next week is finals week. So just keep your eye on the ball for a little bit longer. Stay focused, work hard, and finish strong. Then we have a nice break. We can relax and catch our breath and recover. Okay, a couple of things I still need to go over that are material from the chapters that will be covered on the exam. Probably not too much. And then the rest of the lecture today will be new material that will not be on the exam. So chapter 14, the material I listed here on the goals for the lecture, chapter 14, will not be on this exam, but it will be on the final exam. So a little bit of material here today. We're going to talk about motors and generators. That's part of the material that will be on the exam Friday. But then we'll, okay, good. I thought I forgot to unmute myself for a minute, but no, I think I'm good on my end. I think I'm good on my end. All right. We're moving on. So a couple of things from the material that we're still working on, chapter 13. I want to talk about some applications, interesting applications for some of this stuff that we might not recognize. And I also wanted to show you, we've done this before, but I wanted to show you a little demonstration. If we drop a magnet toward a coil of wire, like this, what happens to that coil of wire? We get a current set up in that coil of wire. What direction? What direction is the current on this side? Out of the page or into the page? Yeah, our magnetic field is down. And it's getting stronger and stronger. So a current gets set up to try to make it weaker. It opposes the change. So the magnetic flux is getting stronger down. So it tries to make it weaker, so it creates its own flux up. So like this, right? That means that loop is like a magnet. In this orientation. So far, so good. What do they do? It slows the falling magnet, right? They repel. What happens after the magnet falls through the loop? Right, a current carrying loop of wire acts like that's an electromagnet that acts like a bar magnet. because the magnetic field looks very similar, right? Now the magnetic flux is down and it's getting weaker. So when magnetic flux is getting weaker, the current tries to add to it, not subtract, tries to add to it. So we would have to come out on this side and go in on this side in order to make its own magnetic flux down to add to this flux because the flux is getting weaker. That means that it looks like a magnet like this. And what do? They attract. But the key here is that it slows the falling magnet. In both cases, the falling magnet is slowed down by this force, which makes sense if you think about it from a conservation of energy standpoint. All we would have to do is drop this magnet in there. If there was a force down on the magnet, it would, if we created a current that caused a force down on it, it would just keep creating its own current, right? It opposes the change that created it. It's an energy conservation thing. If we want to keep this thing generating, we have to put in some force. We have to do some work on it. Okay, let's take a look at it. I will try to demonstrate this for you. Instead of using a single loop and dropping my magnet, I'm going to just use a whole bunch of loops put together. And it doesn't matter where the magnet is, right? If the magnet is in the middle here, dropping, if the magnet's in the middle there, the ones above are attracting it and pulling up. The ones below are repelling it and pushing up. And so the force should be up on it no matter where it is. But instead of using loops like this, I'm just going to use a solid conductive pipe. As long as it's a conductor and a magnet doesn't stick to it, this should work for this demonstration, right? So copper or aluminum. I have a short length of copper pipe and a penny. When I drop the penny, it falls and hits the table in a very short amount of time. Even going through the copper pipe, it falls in about the same amount of time. Here I have a very strong magnet. First, I'll show you that copper is non-magnetic. A magnet will not stick to it. But dropping it through the copper pipe, it takes much longer than the penny. Let's drop both together. Once more in slow motion. This is the same demonstration but using an aluminum track instead of a copper pipe. First I'll drop the penny and you can see it slides down very quickly. This is a strong magnet. Aluminum doesn't stick to a magnet. But when I release it, it slides very slowly compared to the penny. As you can see, it doesn't stick to aluminum. It drops right off the track at the bottom. And one more time in slow motion. Okay, so that was the you could see there that the dropped magnet through the pipe much slower. Now that short length of pipe, it's not quite as obvious. I had to do a little slow motion to make it really obvious. But if I get a 3 or 4 foot length of pipe, it's really obvious. You can walk around, get a sip of coffee, wait for the magnet to drop out the bottom. The pipe is like the inductor, right? The pipe is like a whole bunch of coils of wire put together. Okay, an interesting application are those GFIC outlets in your bathroom. Ground fault interrupt protected circuit. So how do those work? Any place there's water, kitchens, bathrooms, even garages, because they know you might be using some water in there, usually has these ground fault interrupt protected circuits. So on your house, there are circuit breakers on every line. That's to protect your house, not to protect you. If the line draws too much current, what's going to happen to that wire? It's going to heat up. You might get a fire, right? The house might catch on fire. So if the line draws too much current, the circuit breaker trips off, shuts off that line. Now you have multiple outlets. You don't have every outlet in your house isn't on one circuit breaker, because they know when they build houses that you're not going to use every outlet at the same time. So they run a number of them on one circuit breaker, a number on another circuit breaker. If you happen to have multiple things plugged in to outlets on one line, on one circuit breaker, and they're all on at the same time, right? Somebody's running a vacuum cleaners take a lot of current. So if somebody's running a vacuum cleaner and a hair dryers take a lot on the same line, you're probably going to trip the breaker. But that doesn't protect you. The ground fault interrupt circuit protects you. And the idea is, if you have your line, your current, there's two lines there. Current should not get used up going through a device, right? We know that by now. Whatever current goes in one side of a device comes out the other side. It's a complete circuit. Current does not get used up. So if you have your two lines running to whatever it is, your hair dryer, the current going in should equal the current coming out. What they do, these two lines are close together, right? They're sandwiched in a one sleeve, right? The two wires have some electrical insulation around them, and that's in a rubber plastic coating to protect them, and they're very close together. So the ground fault interrupt, they detect the magnetic field around the wires. That's what they're looking for. So you have an iron ring. Which color should I make my iron ring? You have an iron ring that goes around. Like that. Iron intensifies magnetic fields, right? Because the domains align. So what should the magnetic field be around these two wires? Should be 0, right? Because these two wires are very close together, and the current in one direction should equal the current in the other direction. We should have no magnetic field around these two wires. We put an iron core around them. If we get a little magnetic field, that iron core intensifies it because the domains align, right? It makes it a little more obvious to us, so it's easier to detect. What do? We put a sensing coil over here. We wrap a coil around this. And if magnetic field all of a sudden shows up in that iron core, that sensing coil detects a little bit of voltage, right? That's Faraday's law. It picks up some magnetic flux, we get a little voltage, we can detect that. So if, let's just recap what's going on here. If all is well, I1 equals I2. There's net flux equals 0. In the sensing coil. But if the current finds another path to ground, if the current goes into the device, into your hair dryer, and finds another path to ground instead of going back to the source on wire 2, where is that path to ground? Probably through you, right? That's the problem. Probably through you. So if the current finds another path to ground, that means that I2 is going to be less than I1. So now we get a net flux, not 0, in the coil, right? And it shuts off the current going to your device, your hair dryer, whatever it is. This happens very quickly, and it can detect small differences. So like I said, the circuit breaker on your house takes a big amount of current to trip that. It takes 15 amps to trip that. 15 amps, if you're waiting for that to save you, you're going to be fried by the time that thing trips, right? That's a lot of current, do a lot of damage. But these ground fault interrupt protected circuits trip very quickly. A small change in current between the two lines, and they shut off very quickly, and that might protect you. How would it shut off? I don't know. There's just some kind of, I don't know the mechanism for shutting off the current. All right. So interesting application. Of course, the other another interesting application is wireless chargers, right? So if you have an electric toothbrush, you probably have wireless charging. Why? Because an electric toothbrush is used near water. Now, pure water is an electrical insulator, but we don't have pure water coming out of our pipes, right? The water runs through metal pipes. picks up ions and things, metal particles, and water is slightly conductive that comes out of our pipes. So what we end up with is anytime you're around water, you have to be careful, because if you're standing in a puddle of water, now you're connected to something that's slightly conductive. That's dangerous, right? If you're handling electricity. So electric toothbrushes are meant to be used around water, rinse them off, things like that. You don't want to have open leads at the bottom where you hook up your power to charge your battery, because they might short out. So it's all sealed. And you set it over a base. What do they have in the bottom of your toothbrush? They have some kind of a coil of wire. You set it over the base. The base also has a coil of wire. Usually they have a little knob there or something that helps the alignment, so they sit nice and aligned, one on top of the other. And then the coil of wire in one has an alternating field. The coil of wire in the other one gets energized, picks up. We're generating a changing flux in one coil. That changing flux creates an EMF in the other coil, and you charge your battery wirelessly. Same with wireless charging for phones and things. You can get those little pads. What's in that pad? A coil of wire. What's in the back of your phone? A lot of phones these days have wireless charging built in. They built some kind of a coil of wire around the perimeter of the phone. You set that phone on a pad that has a coil of wire in it. And from the principles we're learning this quarter, one wire is changing, one coil is creating a changing magnetic flux. The other coil has a changing magnetic flux passing through it. That generates an EMF that charges the battery. Yeah, the energy goes to the battery. So there's a battery in your toothbrush or in your phone. And when you generate the EMF in the coil of wire that's connected to the battery, it charges the battery. Okay, we've got more, but let's talk about motors and generators. Okay, we need a magnetic field. So we have some magnets create a magnetic field. In this region, magnetic field's gonna look something like this, right? We need a coil of wire. Our coil of wire will sit in here. I'll sort of try to draw it in something like that, right? Coil of wire. And then what we do is we put in mechanical energy. We turn that coil of wire, we put in mechanical energy and turn it. And what do we get out? Electrical energy. We hook up this loop, we hook it up to, here, I'll just hook it up to a voltmeter. Hook it up to a voltmeter. And on this side, we want to always hook up our voltmeter we have what's called a brush there. So the brush the coil of wire is rotating, right? Rotating. We want to have electrical connections, but we can't just hook up wires because they'll get all tangled up after a few turns, right? So instead, we have a conductive ring, a metal ring there that's hooked up to our voltmeter. And the part of the loop that comes down, instead of hooking up a wire there, we just have some metal brushes that rub along the inside of that metal ring, make an electrical connection. So as it turns around and around and around, the electrical connection can move freely. It's just some metal brushes connecting to a piece of metal, and it can slide very nice and easily. We do the same thing down here. To this one. You might have to check your textbook for a better image than what I drew there, but you get the idea. You get the idea. Now, if we look top view on this, what do we see? We see a magnetic field. We see a coil of wire. And at some instant in time, we've got current flowing. Like this. Why do we have current flowing like that? Or maybe I should ask you, what direction does the current flow? If it's turning this way, what direction does the current flow? We have a loop of wire, have a magnetic field pointing this way, and a loop of wire that's rotating like this. Is that right? So the magnetic field points this way, and the flux is getting weaker and weaker and weaker as this thing turns. So the magnetic field the current in the loop of wire is creating its own magnetic field that will point this way, that will add to it, right? So it would have to be in over here and out over there. Now what's happening in the next frame? We wait a few seconds and we look back, and the thing is rotated, right? So let me mark one of these. Let me mark, doesn't matter. I'll mark this one. This one is now over here. And then a little while later, it's going to be over here. And a little while later, it's going to be over here. And then we're going to be back where we started again, right? So it's rotated a little bit. Now the magnetic flux is getting bigger. So the current tries to subtract. The current tries to make its own magnetic flux in this direction, which means it has to be out on this side and into the page over here. So far, so good. Now it's rotated a little bit, and the magnetic flux is decreasing So we're sort of this situation again, right? Only it's the opposite side of the loop is now there. This is into the page, this is out of the page. And then this is going to be in and out. And then we repeat. So if I were to draw what this meter, this voltmeter is reading as the loop of wire rotates around, you can see that it would go in one direction for half a cycle. And then it flips, right? This green side of the loop that I highlighted has current flowing one direction for half the cycle. Then it has the current flowing in the other direction for half the cycle. Then it's back this way, then it's back this way. So you see what's happening. The potential you get the idea. The potential is forming a sine wave, right? That's AC. We are generating AC. And that's how we do it. That's how we do it. We rotate a magnetic field in a coil of wire. They actually use, for the most part, they use an electromagnet for this. They don't use a permanent magnet for this, but they do have one. When I went to Hoover Dam, if you ever get a chance, you should see Hoover Dam. Outside of Las Vegas, Hoover Dam, they use the potential energy of the water, right, to come down, turn a turbine. What does that do? That's getting the mechanical energy out of the water, turning a turbine. That means they're turning a coil of wire in a magnetic field. They have one set up with a permanent magnet, and they start that going. And once it's going, they use its energy to make an electromagnet on all the other ones. It must be somehow more efficient to use an electromagnet. But they have one with the permanent magnet so that they can get the other one started. They can generate enough energy to run the electromagnets on the other turbines, and they get them all going and generating electricity. Now we don't, so a lot of our current, one of the reasons we have AC current is it's very easy to generate it. You naturally want to generate AC current when you rotate a loop of wire in a magnetic field. But sometimes we want DC. You can get a DC generator, and it's very clever how they work. You get a coil of wire rotating in a magnetic field, like this one. And you plot that. Well, the first thing you have to do is get rid of the negative part, right? You don't want the potential, you don't want the current changing direction, right? That means the potential has changed or sign. So in order for the current to change direction, here you can see, where is it? Here you can see the current is going one direction, and a minute later, a second later, in the same wire, the same part of that loop, it's going in the opposite direction. The current flipped directions in the loop. That means the potential changed sign. The potential was pushing the current in one direction, and then now it's pushing it in the other direction. It changed sign. How do we get rid of that? Well, you can hook up, instead of having in your commutator, this is called the commutator. In here, instead of hooking up your lead to one side of the loop the whole way around, the way I've shown it, you switch it halfway through. So you have a metal you have one there, and you have one, I'll draw it in red on this side. No, I don't want that. And you have one here. And you have your voltmeter. So one side is hooked up over here, and the other side is hooked up over here. You can see what we did. We took that metal ring that the brush was rubbing against all the way around, 360 degrees. We cut it in half. So now as the brush goes around, half the cycle it's connected to the metal ring on one side, and then it jumps over halfway through, it connects to the metal ring on the other side. Halfway through, it jumps over, connects to the metal ring on this side. So every half cycle, we're switching the leads on our voltmeter. What would this look like? It would look like this. Okay, we're halfway there. We want DC. At least now we have potential always in the same direction, right? Current always in the same direction, but it's changing. We want it to be constant. So what do? They hook up multiple loops of wire and they offset them from each other. So this is one loop of wire. Then they hook up, I'll make it the next one blue. They hook up a blue one here. And the blue one is offset a little bit, so it generates this curve. And then they hook up a red one here. And the red one generates this curve. You get the idea? And you add all those together, and what do you get? DC. So we can generate AC, put in mechanical energy, turn a loop of wire in a magnetic field. We can get out AC. If we keep our output hooked up to the same side of the loop of wire the whole time, we get AC. If we switch it so that it switches, the output switches between the two sides of the loop as it rotates every half turn, we can, and do some other things, we can kind of generate DC. This DC is a little, it's kind of DC, right? It's close to DC. Now, how about a motor? A motor, as far as the physics is concerned, is basically the same thing. Instead of putting in mechanical energy and getting out electrical energy, we put in electrical energy and get out mechanical energy. Let's take a look at what we're doing. We've got a magnetic field, a loop of wire, free to rotate there. That's hard to see what's going on there. Let's just do our top view. Got a loop of wire. All right, so what are we going to do? We're going to put in electrical energy. So let's turn on a current. How about this direction? We turn on a current. Our loop is just sitting there in the magnetic field. We turn on a current to our motor, right? This is a motor now. What's the direction of the force on these current carrying wires in the magnetic field? Yeah, this one is going to feel a force in this direction. This one is going to feel a force in this direction, right? That's going to rotate. We get a torque, our loop rotates. It gets to here. This side, I will put a green paint on this side. We'll put green paint on this side. This side gets to here, and it is carrying a current out of the page. This side is carrying a current into the page. The forces are still in the same direction, right? So this thing keeps rotating. It gets over here. Where's my green one now? My green side is over here, right? Has a current coming out. What direction is the force? Same direction. What just happened? It's not going to keep rotating, right? We have to flip the current to get this to keep rotating, right? We have to make it look like this. Come on. There we go. We have to flip the current so that the force now is up on this side and down on this side. And if we can flip the current, then what's this going to do? It's going to keep rotating in this direction, right? We don't want it to oscillate back and forth like this. We want it to keep rotating around and around and around. How do we do that? We use this commutator, right? As we feed the current in, the brush changes 1/2 of the time. It's getting power from one side, then it flips the other half of the time. It's getting it from the other end of the battery. And that's how we do it. So we can have AC. So this is if we have, there's two ways to do it, right? Two ways to flip the current. One is you put in AC. If you put in AC, the current is going to flip naturally, right? So we could have a commutator that looks like this. We could have one that looks like this and power it with AC and power the motor with AC, and it will flip. AC flips, right? The potential is in one direction, then it's the other direction. The current's going to flow one direction, then the other direction. Or we can use a commutator that looks like this and power it with the battery, with DC. Either way, we can make a motor that works. Okay? All right, let's take a look at this. Let's see, what do I have here? This is a generator hooked up to a little light bulb. In a generator, we put in mechanical energy and get out electrical energy. Now I'm going to hook this generator up to a motor. A motor takes in electrical energy and puts out mechanical energy. On the left is the generator, and the electric energy is going to go into the motor. Oh, wait. No, this one's the generator. Which one is the generator and which one is the motor? They're the same thing as far as physics is concerned, right? In reality, they're designed slightly differently to optimize them for what they're designed to do. As far as the physics is concerned, motors, generators, same thing. One of them, you're putting in mechanical energy, getting out electrical energy. The other one, you put in electrical energy, get out mechanical energy. Now, if I just have a generator all by itself, and the leads aren't connected to anything, so the generator can't create a current. It's an open circuit. Look how easy it is to turn that wheel. But if I connect the leads together so the generator is creating a current, there's a path for the current to flow on the output of the generator. Can you feel how hard that is to turn? It's very difficult to turn that generator. Disconnect the leads. Easy to turn. No resistance. Connect them together so the generator is actually generating electricity. And it's very hard. We have to do a lot of work. We have to put energy in to get that electrical energy out. Okay, why is that? Let's go back and look at the either one. Doesn't matter which one we look at. Motor, generator. Let's look at the generator since that's what we're talking about. We, excuse me. What do? We turn on, we put in a mechanical energy. This is a generator, right? We put in mechanical energy. We start to turn this thing. It starts to turn, and that current gets generated, right? The red dots there and dash we saw, that's what happens. We talked our way through that already once. What direction is the force on the current in this loop? This upper one that I've painted green feels a force towards the top of the page, right? This one feels a force toward the bottom of the page. That is fighting us. We're trying to turn this thing clockwise. We are putting in, this is a generator, we're putting in mechanical energy turning this thing clockwise, a current, as it starts to turn, a current forms, and that current creates a torque in the opposite direction, fighting us. We call that back EMF, because it's it's fighting us. It's trying to push the current in the opposite direction. We're trying to push it in one direction. It tries to push it in the other direction. But if we start to turn that loop of wire, we put in mechanical energy, we start to rotate that loop of wire, and the leads are not connected to anything. No current forms in that loop. So it starts to turn, but no current forms. If there's no current, there's no force opposing us. So we can just push that loop of current around. We get no opposing force. It's very easy. We're not putting any work in. We're not getting any work out, electrical energy out, right? We're not getting anything. We don't have to do anything, right? But as soon as we hook up the leads and current starts to flow, we get this backwards force that's fighting us. We actually have to put in energy. We have to do work if we want to get electrical energy out. We've got to fight that back EMF. Can you think of an interesting application for that, where that might be beneficial? Yes. So the hybrid cars driving down the street, how does a car normally stop? Brake pads squeeze a drum, and friction generates lots of heat, heats up the air around your car. All that energy of motion of your car is dissipated as heat. It's wasted, it's gone in stopping your car. Then when you go to start up again, you have to put all that energy back into your car to get it moving again, because when your car is moving, it has a lot of kinetic energy. What does this do? Hybrid cars that have regenerative braking, in order to slow the car down, it hooks up a generator, right? The generator is not hooked up to anything when the car is driving down the street, no problem. You hook up the generator to the battery, and that back EMF slows it down, slows the car down, and you're harnessing that. You're getting a lot of that energy stored into a battery. Some cars even use supercapacitors, ultracapacitors instead of the battery, because the time frame is pretty short, and it's hard to charge batteries in a short time frame. But a lot of cars use batteries. Very few use the supercapacitors, but it's starting to become more common. Slows your car down. Now what have you done? Instead of just wasting all that energy and dissipating it as heat, you've stored it. Then you can take that energy, use a little electric motor, and kind of get your car started again. Or if your car is all electric, like mine is, then you have the electric motor already. You store some of that energy and get it back when you start back up. Okay, interesting application. You might think that this always hurts us, but if you're clever, you might say, well, wait a minute, what if I'm trying to stop? Maybe this helps us then. And it doesn't have to be electrical energy. This is how we store it now with batteries. But you can store energy mechanically in a big flywheel or something, have it stored mechanically. As you slow your car down, you could have a big heavy wheel spins up and stores the energy as kinetic energy, and then you get the kinetic energy out of that wheel as the car starts back up again. But we do it with electricity these days. This is how it's pretty much done. All right, let's take a 10-minute break. I have one more little thing to talk about, and then we'll move on to new material. Okay, 10 minutes? All right, we're back. One last thing to talk about before we move on to new material, and it's really the same. Principles, the same ideas we've been talking about here so far, and that is something called eddy currents. The applications are interesting. The idea is, and it's eddy like if you're familiar with, excuse me, if you're familiar with streams and rivers, you get these little, they call them eddy currents that happen kind of on the sides, and small currents within the main current of the river. And so that it's the same kind of thing here. We get little currents forming in our conductors due to changing magnetic flux. It's not a loop of wire, but because it's a solid conductor, it acts like a loop of wire. So the idea is, if I had a region of magnetic field here, and I have a solid conductor, and I move it down into this region of magnetic field, as it moves into that region of magnetic field, it acts like a loop of wire, right? What is a conductor? It's, what is a loop of wire? It's a conductor. So as this conductor moves down into this region, what happens? We have a magnet, think of it like a loop of wire. We have a magnetic flux into the page. So a current is going to get set up to create its own flux out of the page because the flux is increasing through the conductor. So we get a current flowing in this direction. Where is it going to? It's going to return outside of the magnetic field. Now let's think about the force on each of these sides. The current on this side here feels a force in this direction, right? I cross B. The current on the bottom section feels a force up. The current on the right side feels a force this way. And the current up here doesn't feel any force, right? It's outside of the magnetic field. So there's a net force in that direction on our conductor, opposing the motion, which we kind of expected, right? You always expect the force to oppose the motion. Let's take a look at what would happen if I had a pendulum. Let it swing down into a region of, of magnetic field. As it swings in, let me just redraw this. I don't need to draw it 8 times, right? As it's swinging in, what happens? We get a current flowing. We get a force in this direction. And what happens as it leaves? As it leaves the region, we get a current flowing in the opposite direction like this. And we still get a force that opposes the motion. The force always opposes the motion. All right, let's take a quick look at this. I've got the video here. This pendulum is made from a thin sheet of aluminum. Since it's aluminum, it's an electrical conductor, but it does not stick to magnets. I also have a strong magnet. We'll position this strong magnet so the pendulum can swing through it without touching it. Stop the video and predict what's going to happen when we release the pendulum. Okay, what's going to happen? It's going to feel a force that opposes its motion, right? Let's take a look. 3, 2, 1. Let's watch that one more time. Now let's rotate the setup 90 degrees and take a look from this angle. As you can see, the pendulum swings through without touching the magnet. Now we'll modify the pendulum by taking it to a saw and cutting slots in it like you see here. Let's try this new pendulum and see what happens to it. Without the magnet in place, it's free to swing back and forth just as the other pendulum did. Now we'll put that strong magnet in place so the pendulum can swing through it without touching it. Stop the video and predict what's going to happen this time. We're not giving it a chance now to form big current paths, maybe little tiny ones. Let's see what happens. 3, 2, 1. It probably damped the result is slightly different this time. Tiny bit. We'll rotate the apparatus by 90 degrees and take a look from this angle. Now we'll make another modification to our pendulum. We'll connect the bottoms of those slots so they don't go all the way out to the end. They're confined within the pendulum. So those are connected together at the bottom. This pendulum will also swing back and forth freely without the magnet in place. We'll position that strong magnet, stop the video, and predict what's going to happen when we release this pendulum. We should be able to form big current loops here. Let's see what happens. Three, two, one. Very similar to the solid pendulum, isn't it? Let's put the solid pendulum back on and take a look at that again. And the pendulum with the connected slots, one more time. Not quite as quick as the solid, but pretty close, don't you think? Pretty close. So if you have those big paths for the oops, I shouldn't have done that. There we go. All right. Eddy currents. And there are other applications for eddy currents, or I guess I should say there are applications for eddy currents. And it's in for braking or damping the motion of something. On the triple beam balances we have in our labs, how does a balance work? A balance measures mass, right? Not weight. A scale measures weight. A balance measures mass. There's mass on one side, there's mass on the other side. And when the torque is equal, we know that the mass, how much mass we have there. So you have to wait for that to become level, because if it stops and it's not level, the torque isn't the same. It has to be level. And it's going back and forth and back and forth. And you don't want to stand there forever waiting for it to damp out and become level. So they have a little fin on the back of at the end of the triple beam balance inside of the vertical wall there. You can't see it unless you kind of poke your nose in, look in at an angle. You can see there's a little aluminum fin that hangs down. So you've got your balance. The balance, is like this. And then you've got this triple beam over here, right? And there's a fin, an aluminum fin and a magnet. And as it goes up and down inside, there's a pivot point here. As it goes up and down inside that vertical, you have to look at a picture of a triple beam balance. You can see that there's a little aluminum fin that hangs down. And so as it goes up and down, it is damped. The motion is damped by the eddy currents, the forces involved, and it comes to rest fairly quickly. And you can see if it's balanced, if it's horizontal or not. And then roller coaster, a lot of roller coasters use eddy currents as a braking system because there's nothing that can go wrong. You have magnets mounted to the track. You have a piece of metal, little fin that comes down from the bottom of the roller coaster car. And as the car comes by, it slows down because of the interaction with the magnets. Nothing mechanical can go wrong. And so a lot of roller coasters use this kind of braking system to slow the cars down. All right. Okay, we're ready. So this is the end of the material for Friday's exam, but we need to cover some new material. All right. We've talked about this. So it's basically the same thing we've been talking about. I'm not sure why we give it a different name. But what happens is, and the problem here is that we're only really thinking about DC circuits so far, right? We're only thinking about DC circuits. If we have a circuit, a DC circuit, simple DC circuit, and we close that switch. Let's think about what happens the instant we close that switch. We close the switch. Current begins to flow. What does current do? Current creates a magnetic field. What does that magnetic flux that just appeared do? Increasing flux creates an EMF. Or current, if you prefer, in the opposite direction. We call that back EMF. Or self-inductance. Self-induction, sorry. Why self-induction? Because it's a self-induced EMF. The circuit itself caused this back EMF to be induced in the circuit. And what is it equal to? It's equal to minus n change in flux with respect to time. Again, this, because we've been thinking about DC circuits for 9 weeks or whatever it's been, this isn't really a problem, because once you close that switch, things stop changing. The current becomes constant. The magnetic flux through the circuit itself becomes constant, and a constant magnetic flux doesn't create an EMF, and it doesn't do anything. It's only that instant you close the switch. The current has to be changing. Well, when would this be important? It would be important in an AC circuit. In an AC circuit, the current is constantly changing. It's never the same. The current changes continuously. And so for AC circuits, things like this become more important. The other thing is that it causes the circuit to be, I don't know what the terms people use, sluggish. Some people say it's like inertia, for the like electrical inertia. The circuit resists changes. Well, that might be a desirable effect. Maybe you want the circuit to be sluggish. Maybe you want it to resist a change. How do you magnify this effect? You include a coil of wire, right? You include a solenoid in there. Now, for some reason, we like to call coils of wire by a lot of different names. And if we're using it in a circuit to achieve this effect, we call it an inductor instead of a solenoid. But it's the same thing. Ideal solenoid. And so what you end up with is this self-induced EMF oops. Where L is the inductance. And the inductance for a solenoid is N times the flux over I. Units for inductance are the Henry. It's a volt second per amp. And our symbol is just looks like a coil of wire because that's what most of them are. Typically a large coil of wire. Okay. So we've done this a little bit in lab. Had an L, an R, an EMF source, a switch. What happens when we close that switch? The inductor pushes back, tries to push back. This one is pushing this way, right? The battery is pushing this way, and the inductor is pushing this way. And so at that instant, when you close the switch, what happens to our current in our circuit? We get 0. And then as time goes on, it ends up just becoming the maximum current, which is just the voltage over the resistance. Because what is an inductor when nothing is changing? It's just a wire. It's just a wire. It doesn't do anything. It doesn't add anything to the circuit when nothing is changing. When something's changing, when the current's changing, that's when it acts like a source of EMF, either backwards or forwards, depending on whether the current is increasing or decreasing. right? So if we remove, this is increasing current, right? And if we decrease, we do something like this, where we remove the battery. We remove the battery from the circuit. So we had current flowing this way. We remove the battery, that current starts to die down, and the inductor says, wait, I don't want it to die down. I want to keep it the way it was. It acts like an EMF source in this direction, and it tries to keep pushing the current. So instead of the current just dropping to zero almost instantly like we would expect, the current does something like this. It stays at its maximum value for a little while and slowly goes to zero. Yeah, you could use Lenz's law to describe that, sure. So our formulas, what are our formulas? Increasing current, I is I maximum. I'll just write I maximum. You can figure out what I maximum is, right? 1 minus e to the minus t over tau. And tau now is L over R. Our time constant is L over R. And down here, we get I is I maximum e to the minus t over tau. Okay. What's more interesting, though, is the energy. Yeah, just Lenz's law is good. It's, you know, whatever you're using, whoever you're thinking about, Faraday's law, Lenz's law, it's all the same stuff. This falls right into that category. Okay, if we go around our loop, we've got the EMF is equal to IR plus L di dt. If we multiply through by I, we have I E is I squared R plus Li di dt. What is this first term? I times V, potential. We're using the script E for EMF, but it's potential, right? Power. IV is power. What's I squared R? power delivered to the resistor? What must this be? That must be power being stored in the inductor. All right, so if energy U is our energy, du dt is power, right? So du dt, we don't want power, we just want to think in terms of energy. What do we end up with here? We get U is equal to 1/2 Li squared. Energy stored in an inductor. The inductor stores energy in the magnetic field. A capacitor stores energy in the electric field. And what is the energy stored in a capacitor? Just for refresher, 1/2 CV squared. Very similar, right? The formula is very similar. If we just have an LC circuit, if we just have an LC circuit, we got a capacitor, an inductor. The capacitor starts out fully charged. I'll draw out we've got at t equals 0, we close that switch. So it looks like this. The capacitor is fully charged. And I is 0. And B is 0. And Q is Q max, right? All the charge is on the capacitor. Then what happens? A little bit later, current is flowing and it hits its maximum value when the charge on the capacitor goes to 0. The charge goes to 0. I is equal to I max. and B is equal to B max. The magnetic field in the solenoid is proportional to the current, right? The more current, the bigger the magnetic field is in there. And then a little bit later, I'm going to run out of room here. That's okay. A little bit later, this is charged up in the opposite orientation. Q is equal to Q max again, but in the opposite orientation. I is 0, B is 0. And then a little bit later, it's going the other way. Oops, forgot my inductor. We've got I is I max, B is B max, and Q is 0. And then we're back to where we started. Okay, what's happening here? It's an oscillator. You see that? It's like a pendulum. I have a pendulum. I have a pendulum here. I start out, my pendulum has no kinetic energy. All the energy is gravitational potential energy. I let go and it swings down, and at its lowest point, it has no gravitational potential energy. All the energy is kinetic. But it swings through that point. It has inertia, it keeps going, and it gets up here where it has no kinetic energy. All the energy is gravitational potential, and it comes back, and it oscillates back and forth like that forever if there's no air resistance, no friction. Same thing is happening here. If there's no electrical resistance in this circuit, the energy oscillates back and forth between the capacitor and the inductor, the capacitor and the inductor, and it oscillates back and forth like that forever if there's no resistance in the circuit. If there's some resistance, then it's a damped oscillator, right? The amplitude gets smaller and smaller and smaller as it oscillates back and forth because some of the energy is being dissipated into the resistor, into heat. And what we end up with so you might have to think back to harmonic oscillators with 4A. Anytime we have the second derivative of something equals some constant times that same thing again, sines and cosines are the simple solution to that, right? We know sines and cosines work. And in this case, what you end up with, you could check your book here, the second derivative of the charge with respect to time is minus 1 over LC times the charge. This is a function of time, right? Well, what satisfies that? This does. Omega is the angular frequency of oscillation and the phase angle is there to set initial conditions. because if I choose a cosine and you choose a sine function, they both satisfy this differential equation right here, right? Sines and cosines. Well, what's different? We get a different phase angle because sine plus 90 degrees or minus 90 degrees gives me a cosine, right? So we just change that, and that makes our equations match the initial conditions of the problem. I think the easiest thing, let's just do a simple problem. And we'll kind of see it in action here. We've got a simple circuit. Oh, there's a switch here. There's a switch here. Now, we've talked a little bit about capacitors. What happens when you close that switch? The capacitor acts like a short. There's no charge on it yet. Charges can flow into it very easily. But after a long time, the capacitor is an infinite resistance. The inductor is exactly the opposite. The instant you close that switch, when there's a big change, an abrupt change, the inductor acts like an infinite resistance. But after a long time, it's just a piece of wire. It's just a short. So in this case, our switch is closed for a long time. After the switch is opened, the V maximum on the capacitor is 150 volts. What is L? And we are given the fact that E, R, L, and C, E is 50. L we're trying to find. R is 250. Switch closed for a long time. So what's going on? If the switch is closed for a long time, what's the current in the circuit? What's the charge on the capacitor? Let's find our initial conditions. What happens? What is happening the split second before we open that switch? The circuit looks like this, right? I could draw the capacitor in if I wanted to. my current takes this path right here. And what's the charge going to be? 0. It is shorted out. Has no potential difference across it. No charge in the capacitor after a long time. And what is I going to be? What is it, 50 over 250? All right, now, what's the energy at that time? From the split second we open the switch, the energy is not going to change, because when we open the switch, we have this circuit. No resistance. We had a current going through here, so it tries to keep that current flowing, right? And it's going to charge up the capacitor. So at t equals 0, when the switch is opened, oh, sorry. Constant. So when the voltage on the capacitor reaches its maximum, then all the energy is in the capacitor, right? We good with that? When the voltage on the capacitor reaches its maximum, all the energy is transferred. So at t equals 0, all the energy is in the inductor. When Vc reaches its maximum, all the energy is in the capacitor. So the energy in the capacitor, 1/2 CV squared. I get 5.625 millijoules. And then we say that 1/2 Li maximum squared has to equal that. And we get L is, we know what I maximum is. L is 0.281 henries. Okay. Anyway, take a look at this at some point. You're probably going to focus on your exam most of this week, but this weekend, start focusing on this stuff because you're going to see this the following week. All right, lab. Today, no lab this week, right? No lab this week, but I'll tell you what I'll do. I'll log in at 12:15 and see, I'll just run it like an office hour. If there are questions, we'll deal with that. If there aren't, we'll end it. And then we'll do our normal 4 o'clock office hour. Sound good? Okay, So if you're interested, anyone interested in joining an office hour at 12:15, we will do that. Otherwise, we'll see you later.